polynomial commitments. And then we have lightning talks by members in the audience, and some talk by Anka on theonomic proofs in blockchains. I guess it also uses pairing-based SNARKs. Yeah, so it's want to think of a joke, but I think someone said you should always start with a joke, and then others say you never start with a joke; it always goes wrong. But things go slightly wrong for people are still coming in. So my self-deprecating point is that today the women are taking over, and that's why you get like a white male session here. Yeah, and another, like I start introducing Carla. So Carla is associate professor at the engineering department of the University of Pompeu. How do you pronounce it? Pompeu, Barbara. And she got a PhD also in Catalonia at the Polytechnical University. She was a postdoctoral researcher at the UNESCO chair in data privacy. That's Universidad de Tarragona, another region in Spain. And also very importantly, at the foundations of photography group at the Ruhr University of Bochum. And I think that's really her adopted home, because she's more German in nature and spirit than myself. I'm Austrian, for those that suspect something. And she's interested in theoretical aspects of public key cryptography, as well as kind of cleaning up the mess of pairing-based SNARKs, and see how that goes. I think that's how I understood it. And so improving group-based zero-knowledge proofs. That's the right way of saying it. And yeah, the floor is yours.
I guess I just have a question to start. So why do you think that the women are taking over is a joke?
No, it's serious. It's serious.
Okay. So
the joke was about me being kind of the minority representative.
Okay. Okay. So Markulf announced we're going to talk about pairing-based crypto, and actually in this first lecture there's no really pairing, so the way I divided the lectures is in general I'm thinking of a group. In the back of your mind, of course there's an elliptic curve. That's what we use nowadays for group. And of course these are groups where the discrete logarithm problem is hard. Right, so we have that no adversary can efficiently compute the discrete logarithm of an element if this element is like randomly chosen. And we are in a prime order group, and in the first talk I would talk about the techniques that we have in groups without efficiently computable linear maps or pairings. The second, I will focus with when we have pairings. And this is like the lecture of Arantxa. Okay, so she will talk about polynomial commitments. So you will see that in this talk, I will now and then talk about polynomial commitments, but I won't really go into it because this is like coming after. And you see that I like to focus on techniques, okay? Because I think that if you try to follow what's happening in group pairing SNARKs, like there's like papers on ePrint every week. So we are all trying to follow what's new, what's happening. But really, if you dig a bit deeper, often the techniques are more staples. So I think this is what you should focus on if you want to get some orientation about everything that's happening. So for this first lecture, I will first talk a bit about commitments, like very old stuff. So here I just mean like normal commitments, like old type of things. And then I will talk about bullet proofs, which is a way to have a sort of a proof system that's quite efficient in terms of communication complexity. And then I will briefly introduce a notion, like mostly the idea, because that's way too advanced to go into, of what is an accumulator. So first, commitment. So that's really like textbook sort of thing. That's like Pedersen commitments. Everybody knows Pedersen commitments. I think And actually, when you're really in a group where you have no pairings, there's not much more you can do, right? Like the only way you have to commit to a vector is if you want to commit to a vector of n elements, the only thing you can do is essentially you have a key, which is also a vector of group elements. Here, I parameterize this by some distribution because for some reasons you might be interested in different distributions of the keys, but essentially you cannot do much more apart from freely choosing the distribution of the key that you want to use. And how do you commit? So you have these group elements and you have this vector of field elements and you just do a random linear combination. I'm using all the time additive notation with, I hope Benoit forgives me for this. Okay, so we're doing a random linear coefficient. So essentially means we're embedding these exponents inside the curve and doing this. Okay, so if you're starting in crypto, maybe you're more used to see the Pedersen commitment in multiplicative notation. Okay, so why is this binding? Well, what would happen if an adversary was finding two different openings? Well, the adversary, well, I didn't say this, but an opening is anything that satisfies that, right? Like you're given a commitment, if you can provide an opening, means you're able to find some vector m such that this is true. So what would happen if an adversary could find two? Well, the adversary could actually find a vector of field elements such that the inner product with the commitment key is 0. How we would call this problem? Sometimes it's called the find rep problem, find representative problem. It's a really old problem. This is from '96, something from a paper from Brandt. And now also people use it kernel problem or discrete log relations problem. Why? Because we're trying to find somehow, this is a vector of group elements for which we don't know the discrete logarithm, and we're somehow finding a non-trivial relation or a non-trivial representation of the 0 element. Okay, so this 0 is not the field 0, this is the point, maybe it's not the best rotation. So this is the neutral element in the elliptic curve, okay?
The commitment is a vector of group elements and C, or is
It's one element.
the vector of group elements is publicly known, or?
The commitment key is public known, this is hidden, right? Like you only see that, and this is like the commitment to something that is hidden.
Wondering about the GIs.
The GIs,
They're part of the commitment.
they are the key. It's zk, it's a commitment key. Everybody knows the key that you use for committing, and okay? And the only thing is that you can use different types of keys parameterized by this distribution. Okay, what do we know about these? So like the first thing is that obviously this problem.
It's actually maybe a nice exercise, how it would be insecure if you were part of the commitment, how you would attack it.
Okay.
Think about it.
You could recompute everything, right? If you. What do you mean? No. I don't know what.
And you could choose it such that denote a discrete logarithm, right? If you make it part of the commitment,
yeah.
just choose your own
Yes, of course.
GIs.
Yeah, everything. This is binding because this was actually what I was going to say next. That of course this is a problem that is easier than the discrete logarithm problem, right? It's a necessary condition that the discrete logarithm problem is hard. If you can find the discrete log, you can solve this.
You can prove equivalence.
No, we're getting to this. So actually, I wanted to show this, but for now, it's easy, right? And so this is what we see next. So we see exactly this, that actually it's equivalent, right? So we can safely say that when we use a uniform key, then really this is an equivalence. So if you break the discrete logarithm, so what this means is that this is also an easier problem than the discrete log. So at the end, we have both implications. So and this is a type reduction. And I think the trick is important to show you. So I will show you how you do this reduction. Okay, so we want to show if this assumption is not secure. So if you can find a representative, you also can break the discrete log. That's like really sort of textbook. So maybe that's why Jonathan already. Okay, so why we have an adversary that can break this problem? and we want to build an adversary that breaks a discrete log. So this adversary against the discrete log gets this challenge. She's trying to find the X such that this is true. So what does he do? So he chooses two random vectors of size n, and he creates this vector of commitment keys. Okay. Now it sends this commitment key, and it gets a solution to the find representative problem. So it gets a vector b such that this is equal to 0. Okay. And then my claim is that what he can answer is this value x. Okay, why is this the case? Well, if this is 0, since G is a P plus BH, then we can isolate, so we can isolate H in terms of P, and then we know that this is the discrete log. Okay, so I put a star here because there's a thing here. So what's the thing here that I didn't mention? What can go wrong? Divide by 0. Exactly. So the problem could be that this could be 0. Why is this not? This cannot happen, or only with very small probability. That's the question.
You don't know B, and B is taken at random.
Well, because what the adversary sees completely, actually, information theoretically hides A and B, right? And that's the reason why I'm making this reduction is because this is like a useful trick. It appears in several times whenever you want to try to reduce things to discrete logarithm setting. What you put is like you embed the challenge, whatever the problem you want to solve, information theoretically in the things you feed to the adversary. Okay, so what we're using here is exactly the Schwarz-Siepel lemma. Okay, so the adversary doesn't know B, so the probability that he can find a B that really maps to 0 is exactly 1 over B. Okay, because it's like you have to think about this as a sort of multivariate polynomial of degree 1, and this is only 0 with probability. Okay. Okay, so that's very old, and I spent already 28 minutes. Okay. I know, only 10. Okay. So the thing is, now we could change the key, right? So like we could think, what happens if I use structure? I call this sort of structure keys. So it's not uniform. I'm using different structure keys, which are powers of some value, for instance. Or I could also think of having somehow multilinear. These are all the multilinear monomials with mu variables as my key. Okay. So any idea? So would this be well, maybe it's too hard to say, but what you have here is that you can do the same trick, okay, and embed and do a reduction to another problem, but this is the n discrete logarithm problem. Okay, what's the idea? So the idea is you would do the same trick. You embed in each of the variables information theoretically, the challenge. But now what has changed is that when you embed in this point here a challenge, you need to have a degree n. So you need to have n powers of your challenge to be able to simulate all this key. Okay, so a priori, this like the thing here is that if we have a uniform key, we are better because we have weaker assumptions. Okay, you can see that the first one is equivalent to discrete log, the second one is equivalent to ND log. Okay, so it's more desirable to have this from a security perspective.
It's the same assumption for 2 and 3.
Yes, because actually, yeah, that's a good point, because actually this shows up later, for instance, in the proof of growth 16 also. What matters is the total degree of the challenge you're trying to do. So of the things you have to create. Okay, so you would prefer the first one because it's weaker assumption, but really for SNARKs, I have a disclosure to make, because nobody cares about these weaker assumptions. But why would we prefer the first one? Any idea?
Viable.
It's equally falsifiable. They are both.
It's weaker, but also it's transparent.
Yes, exactly. So like the second point is that for pairings, nobody cares about this reason for going, so for SNARKs, for this reason for going for the same key. But people care about the fact that actually you can sample the first key in a way that nobody knows the discrete logarithm. Okay, so you can like put you have like these hashes that map to group elements. And if you put like something that has enough entropy here, like you could sample in the group without knowing the discrete logarithm. Whereas to sample any of these keys, you really need to have a relation between the things that you're sampling, and then you don't know how to do it. Okay, so there's lots of economic reasons to prefer that, and this we don't care. But now the final question is, okay, but so in principle, all this says actually there's no reason to go for the first one, right? For the second and third one, because the first one is much better. But the question that remains is, could we get some extra functionality from having this trusted setup? Okay, and in the second lecture, we will see that this is the case. Okay, if we have pairings and we have this better, this SRS with more structure, then we can exploit that and be more efficient. Now, my question to you is, do you think any thoughts about what happened in the group setting? Do you think this can be exploited? Actually, it's not a formal argument, but I leave it open to discuss in the break. Okay, so the disclosure is, I think there is like a sort of informal argument that says no, you cannot do that, but I would be happy to discuss this. Anyway, for the rest of the talk, think all the time we have a uniform key, okay? Because for now we didn't see any reason to use anything else that's not so good. Okay. So now I will tell you about bullet proofs, which is like basically the most famous proof system in discrete law proofs. And the way we think of bullet proofs, we could write it in different ways, but I will stick to how bulletproof was originally formulated and how people think about it. So we have a group of prime order as usual, and we have two pairs of commitment keys. Again, Pedersen commitment, nothing fancy, okay? And we want to prove statements of this type. We have a group element, and we claim that this is a commitment to a vector A with key G, and we have the statement consists of three parts, T, D, and sigma. We claim that D is a commitment to B with key H, and we claim that sigma is the inner product of these committed values. Okay, again, this sort of only makes sense sort of in a domain of proofs of knowledge, okay, because this is like completely shrinking. So essentially you could always find some A, but like the adversary has to show that it knows. So the statement is C, D, and sigma, and the adversary has to show that it knows an A, it knows a B, such that C opens to A, D opens to B, and sigma is the inner product of these committed values, okay? So written mathematically, this looks like something like that. C is the inner product of AG, D is the inner product of PH, and sigma is the inner product of A.
That's a quick question. Does it matter if G and H are different, or it's just
no, it doesn't matter. But so it plays a role, and let me tell you in a second why. Okay. Okay, so and the core of the bulletproof strategy is a recursive strategy. Okay, in some sense, you have to think that in the discrete log setting, we can really not do many things apart from opening commitments. Okay, so the strategy that works is just trying to reduce the problem to a smaller problem, so that we are making the problem smaller and smaller until we get to a point that we can just check that without breaking successively. Okay,
I'm afraid of getting lost. What's the purpose? Like, what are we doing? We have this, like, reducing it to a smaller problem, but what the focus? We have like these commitments now and,
Yeah, so the statement informally is, I have a committed value, I have another committed value, and their inner product is a certain field element. The inner product is 3. So that's the statement. So and if the question is, why do you want to prove that? I won't tell you now. So we come back to the second lecture. No? So what is that? It's not clear. So in general, you can think of proof systems as proving things about things that are hidden. Right? So here I have something that is hidden, and I want to prove something about their inner product. It's a theoretical problem. Okay? So of course I can give to the verifier, I can give the verifier A, I can give it B, but of course, that's not the point. First, because of zero knowledge, but actually I won't be talking about zero knowledge, so let's forget about zero. But it's for succinctness. So we want all the time, I didn't mention because in the second lecture I will talk a bit more about what are SNARKs, but what we want is that the verifier does very little work. Okay, so we want to convince him in that, and it should be doing work that is sublinear in n sides of the statement.
prove that these relations hold with all the opening commitment.
Yes. Yes, okay. Exactly. Okay. So what I can do is like I keep reducing it to smaller and smaller and smaller until it gets to a point where I can open it and the verifier still has to do very little work. Right? So we agree that once I open the commitment, the verifier can check everything. Okay? Okay, so we are reducing this to a smaller statement, and note that the smaller statement change is, so we have new values C prime, D prime, and sigma prime, but they are also committed with respect to different keys. Okay, I will see how to do this in a second. Okay, so really this recursive strategy is based on a few simple facts. And this is really simple, I don't know. Okay, so first fact is if you have C, which is the inner product of A and G, right? Of course, it is the sum of the first part with the first part and the second part with the second part. Right? So if I have an inner product, I'm doing the first part of the an inner product of the first part and an inner product of the second. Okay. Second simple fact. If I have some scalar, okay, and if I have so let's say I'm splitting again, AL and AR are left and right part of A. So if I do a combination of so if A prime is a combination of AL and AR with coefficient alpha, and G prime is a combination of the left part of the key with the right part of the key with coefficient alpha -1, then the product of these two values is equal to this. Okay, this is nothing but expansion. Okay, so let's write this. So if I'm doing the inner product of this with this, what happens is that there are two terms that have as coefficient 1 because alpha and alpha -1 cancel. So this one with this one cancels. And, oh, sorry. This one has coefficient 1, this one has coefficient 1. There should not be a parenthesis, should be here, but this is 1, it works, okay? Just expansion.
What is CRL?
Okay. Sorry, I didn't say it, but it's this, and this is this. It's like the commitment to the ref light. It's like the cross terms. Okay, usually these are referred to the cross terms. This is the cross terms, cross terms.
Are you sure that the size are compatible? I mean,
No, we don't check anything.
okay.
No, so for now there is no. So this is just mathematical facts. Yeah? There is no adversary here.
I'm going to assume that left and right are equal in this size.
So I didn't say this, but like you're splitting your vector in two. There's a left part and there's a right part.
You know, same size.
And they are same size,
Same
yes. Okay, yes.
In this A prime, so basically it's half it's a vector of half of the previous.
Yes, exactly. So this will be, it's a linear combination of vectors of half the size. So this is a vector of half the size. This is a vector of group elements of half the size. Okay. So anyway, so if I have a new way and a new G that I construct in this way, the new product is the thing that I already had, the C that I already had, plus some cost terms. Okay. No, nothing for now, just expansion. Okay, and now I will answer Jonathan's question before. So actually, I'm interested in doing a little bit of an aesthetic change to my statement. So I put things on the same side every time. Okay, so C is a commitment to A and D is a commitment to B, but I am interested in like writing B always on the right side. Okay. Now, so now I can apply the same thing here to all these elements. All the things that are on the left side, I put alpha. All the things that are on the right side, I put alpha minus 1. Okay, and if you do this, well, you're doing a product, so you get the same thing for all these things. Okay. They mean different things, okay? But this always means like the first part, the right. So the first, this would be the first, the right part of H, and the left part of B. Okay. But you're just repeating 3 times the same thing. If everything is in the same side, then it works exactly in the same way.
How does that answer Jonathan's question?
Okay, because I'm interested in B being on the right side because here B appears here prior to B. Okay, so in some sense, the combination that I do for B is different. Okay, I'm not combining A in the same way that I combine B.
Yeah, but you could have
Okay.
G prime on the left.
Yeah, but imagine you start. No,
I guess maybe the point is that even if you start with G and H being equal, after
Exactly.
the first iteration, they won't be equal anymore.
exactly. This is what I.
Yeah.
So you start with G and H the same, but now the new, even though if G and H are the same, but here G prime, so H prime and G prime are not the same.
That makes sense. Yeah.
Okay. Okay, so it's just like my point is that this is doing 3 times the same thing. Okay, so for the purposes of the protocol, I will just simplify the statement because essentially I hope this convinces you that I'm proving 3 times the same type of state. Okay, so
But they are slightly different, right? The A prime, B prime is in a different, these are field elements.
yes, but all that matters is the linear structure, right? Like it doesn't really, so if you think about the protocol, like somehow information theoretically, what you do with each element, you're doing the same thing. Okay, so anyway, the point is from these simple facts, I immediately get something that I think it's a good way to remember what this protocol does, to call it split and combine. Okay, so you get this interactive protocol. You start with a statement C, and you say your statement is, I know an opening of C with respect to the base G. Okay, what do you do then? Well, then you send to the adversary these cross terms, CRL, you send C, CRL, CLR, and then you get a challenge, okay? And then your new statement will just be this, okay? And this is like a shorter statement, okay? So it's like you're splitting your statement in 2, you're taking care of the fact that there is like some bilinear operations, and then you construct a new statement, okay? So, and if you can do this, like when you're thinking that you're proving the real protocol, like you're proving these 3 things, you could think that you could do this in parallel for all of them, but in reality, what you do is really batch this. So you do it in a concise way, so it doesn't cost you more, but you're doing that essentially 3 times. Yes.
Why do you send C as over as well?
Sorry?
Does the verifier know C already? If you go,
Yeah, it's part of the statement, but I put it that he sends it, but yeah, it's the statement that he wants to. So the statement is, I know an open C.
in the way the verifier already knows that. If you go back,
Yeah, the verifier already knows it.
so you don't need to just know C, and then also he computes the new C prime and also knows
Yes.
that.
Yes. Okay, and the prover himself, he computes as, he has like also a shorter witness.
On the previous slide, you had proving knowledge of commitment to A to B and thinking about their inner product. Are we just considering?
So what I'm saying is that this is essentially proving the same statement. So for simplicity, I will focus on showing you one because it just gets messier, but it's the same thing. Okay, so here's the full protocol. I want to put it because otherwise things get a bit too abstract. Okay, so the full protocol, you imagine you have C, which is like a vector of 4 elements. And you start by having these cross terms, you send them, you get a challenge, then you get like a smaller key, G1, you have a smaller witness, then you compute the new cross terms, you send them, you get a new challenge. And finally, in the last round, you have that C2 is just and I wrote it as an inner product, but it's just an exponentiation, okay? It's just one value multiplied by an element in Z, okay? And so what does the verifier do in the last round? As Markov said, he knows all these statements and he receives A2 and G2 and he checks that this opens correctly. The important thing is that this is not sufficient. It also has to check that G2 is correct, okay? So I put it here because for a reason, because I think it's like in some sense, it helps me to explain things, but actually the verifier, the prover doesn't need to send G2, right? The prover can, the verifier can compute it itself by just doing the same thing that the prover is doing. There's nothing secret here. Okay. So this is very important that you remember this consists of this, the last check consists of 2 things. Okay, checking the final opening, which is of size 1, and checking that G2 is correct. Okay. Very briefly, because I just want to give the idea, not to be too formal about soundness. How will soundness work? Well, the idea is that first, in the original bulletproof paper, they were proving witness extended emulation, the notion that Jonathan also introduced. But actually, I think that it's a nice way to think about it is in terms of something that's called algebraic reductions of knowledge. This was a notion proposed by Kotapala. Well, somebody help me there, but anyway, it's like a recent paper of last year or something. Like, I think it's nicer to think about it in terms of around what happens in every round. So in every round, what happens is that the main idea is that if you know a witness here, so in the last round, then you can show, so if you know an opening here, you can show that in the previous round, you also know an opening of double the size. Yes.
So here Kotapalli and Brian Pano.
Yeah. Thank you. Okay, so what's the idea? So the idea is like, well, if I get different A2s, okay, so for different challenges, at the end, I get like a system of equations, doing Gaussian elimination. At some point, you can get this witness that has double the size of the one that.
Is it similar to round-by-round soundness? Or?
I don't know, but I think maybe yes, but I don't know. Okay.
Why do you need 4 rewindings here? Can you say?
Because of the system of equation, how it looks like. Maybe I missed it and maybe it's 3, but. So the unknowns are these 2 but then you need to eliminate these things because they are different. No, these are different, so you need, maybe I will check it out. Maybe I did that before, but yeah. But anyway, the point is that this is a Gaussian system of equations, and then you extract a witness that's double as long as the one that you know. Okay, so informally, let's think about it like that. What I'm more interested is first on the functionality of this. Like first, let me show you that this implies polynomial commitments, which I didn't tell you what it is yet, but what is a polynomial commitment? So, well, a polynomial commitment is just like a normal commitment, okay? Except that it has like an additional algorithm. Well, there's like, I'm being quite informal, but there's like an official algorithm that an efficient algorithm that when you give him the commitment key, the witness, and a certain point in the field, okay, it outputs. Wait, there's like typos here. So C. So if C, no, I think here I changed to C. So this should be A. So if A are the coefficients of some polynomial, okay, so you're thinking it's the same thing as before, you're committing to this vector, but you just think of this vector as a vector of coefficients of a polynomial, okay? And what you can do is this algorithm outputs a proof that the polynomial is correctly evaluated at a point of your choice. Okay, so it can convince you that you have evaluated the polynomial correctly, where the polynomial is committed inside this commitment. No? Yeah. Okay. Good. So and I notice that the useful polynomial commitments, the proof of correct opening should be sort of short, right? Otherwise, of course, you can always like just send the whole witness and then you recompute that if it's correctly evaluated. That's useful if it's like sort of short. Okay, so the reason why is that this relates to an inner product statement is because, of course, I can think of a statement that looks like this. I have a committed value, then I have a committed point, and what I want to know if is this value fs is the inner product of the two committed vectors. Okay, that's actually a statement that's too complicated. I don't really need to commit to S. S is a public point. So, but anyway, the statement that I want to prove really is like a sort of inner product statement. Okay, polynomial evaluation is always like an inner product. So I can prove it with an inner product type of thing. Okay.
So S is private.
Sorry?
S is
No, S is public. It's part of the input. So like the statement you want to prove with a polynomial commitment is that given a public point S and f of S, this has been correctly evaluated, where f is the polynomial that has coefficients A.
which is private.
Okay.
We're doing it in the same way as we did like in the previous problem.
Yes, so you
Because
can execute this here,
the-
except that you don't need to send anything
Does it
related to
really-
the.
Does it somehow, can we explain what happens in unrecursive iteration where we halve the problem size? Is it like we evaluate the polynomial that many points?
So it's really
That many variables and
so so it's really like the same as here, except that now you would be proving that C is equal to this. You also have a point S, okay, which actually well, I think you don't really need to do anything with S because at the end you know S, so you could compute anything that the verifier can compute anything on its own related to S that comes at the end, because it will only depend on S and the challenges. Okay, but let's forget about this. So let's say that you commit to S in the same, to the powers of S in the same way you can, okay? You commit to so to the inner product, which is the evaluation of the polynomial. is a field element, but otherwise everything is the same. Like all the operations that you need to do are the same, except that some things are that used to be group elements are field elements. Okay.
So in the bullet proofs, you just prove 3 inner products, and now we just have to prove 2 inner products.
Yes.
In short.
Yes. Okay. So this is one thing. So now the very interesting things is this. Okay, so what do we know about the efficiency of bullet proofs? First thing, the prover complexity is linear. Okay. What does the prover do? So if we look at the protocol, at the end of the day, it's just doing these commitments to these cross terms. Okay, plus some, these are just, well, here also do their operations. But if you sum everything it's doing over, it will be linear. So this was one reason that this is actually how the first paper that did bulletproofs, which actually was not bulletproofs. Bulletproofs is just the how we all know it, but it's a paper of Bootle et al. This is how they were selling their paper. Okay, we have the first linear prover SNARKs because other SNARKs had a higher computational complexity. Okay, for the prover. I guess it's not hard to convince you that the communication complexity is logarithmic, right? Because there's like a logarithmic number of rounds. Now it comes the tricky part. What's the verifier complexity? Okay. So let me see. So here, like the verifier is just sending the challenges. Okay, this will, in reality, if you compile this with Sfiak-Shamir, this is not interactive. This means the verifier will be checking some hashes of the transcript and so on. But the tricky part is here. Okay, so here it's doing a check, but it also has to check that this G value, G2 is correct. How does this G2 look like? So let's unroll it. So we start with a vector of 4 elements in the first round. So now we take the upper half and multiply it by alpha minus 1, right? So this will be, so G0 goes with G2, G1 goes with G3, and you have this. And in the second round, you end up with something like that, okay? So just roll it out. So you have to, it's this term plus this term multiplied by alpha 2 minus 1, okay? So you get this. So, and this actually, it's both these ways are interesting ways of writing this new key. So you can think that this new key is the inner product of the original key times this vector, okay, which is a vector that has size 4, but is actually a tensor product of 2 different vectors. And you can also think of this vector as a polynomial commitment. Okay, how of which polynomial? Well, this polynomial. Okay, there's like this polynomial has exactly the coefficients that you need here. Okay. So on the one hand, we have like terribly bad news, very annoying. It turns out that to check that G2 has of this form, what do I need to do? Well, I need to do 4 exponentiations, right? I need to recompute G0 plus alpha minus 1, 2G. So that's really bad because this means that the verifier is linear. On the other hand, that's sort of like really like tough luck because this is like really not a random, this is really not so it doesn't have a lot of entropy, this vector, right? Like this is not a vector of coefficients that has like super high entropy. So the question is, can we do something here? Is there some way of exploiting that this vector is just not a random vector, but it has like some structure, okay?
What do you mean that it's low? Because it alpha appears all over again, alpha 1 and alpha 2.
Well, I mean, it's determined, like it's a vector of dimension 4, but it's determined by 2 coefficients.
Yeah.
Like, or maybe call it sparsity or something. It's like it factorizes in something.
Can I ask, I mean, in theory, it's true that it's linear, but in practice, it's a multi-exponentiation, which is much faster than n exponentiations.
Yeah, that's true.
So-
I didn't go into this. Still, I guess, I mean, at least
Theory,
here,
it's linear though, even still.
but still, I mean, even like, so Jonathan's point is that here you're computing a multi-exponentiation. I don't know if you're familiar with that, but there's like an algorithm, Pipelinger algorithm, that actually makes it much more fast to compute this a multi-exponentiation that to compute n individual exponentiations. Okay,
It's still O of n.
Yeah, it's still O of n,
But
but
the-
practically speaking, it's like 1 plus little o of 1 or something.
so I thought it was like a log n speed up, like factor or something. That's how people.
Or it's
think
like
about it.
divided by log of
Oh,
something, but I'm
maybe,
not sure of what, of its log of n or. of
Actually,
its
maybe,
log of-
maybe you're right. I'm thinking usually, yeah, I'm thinking of constant number of terms, but if you have n terms, maybe it is log.
I think that it's not, it's still quite bad. And for,
What's the
Is it
benefit of
sublinear?
this?
Do you get sublinear?
sorry?
I think it's a matter of whether you're counting group operations or whether.
Yeah, that's right. So it's a question of whether you're counting like bit operations or group operations. Yeah, bit operations, it has to be linear because you have to read every term.
No, but so we always think roughly in terms of group operation.
Okay. What's the benefit now of this bulletproof then? If the verified complexity is O of n, then I could have opened the commitment immediately. Was that been the same complexity for the verifier in the end?
Okay, so we will get to that. So that's like, indeed, that's like actually real annoying, no? Like this is actually, we're thinking, why did we do all?
I mean, it seems like I just increased the communication complexity now and.
But the communication complexity is lower, right?
Yes,
So the proof is smaller, which is good.
yeah, the proof is smaller. So if you want to store it, if you want to store it, then you, you need less.
It looks like we just looked online. It looks like it's n over log n group operations. So it's slightly sublinear.
Okay, so this is where we come, accumulators come, okay? This appeared in a different context. In the context, this is an idea that appeared in the context of something called recursive proof composition, that I thought it would be too much to get into for this first session, and I think Anka will talk about this too. So I presented this idea in like a sort of different context. Okay, so we are in this position where we have like a SAT world, like we have linear verifier, and this statement that I said generalizes, right? Like I made it 4-4, but like in general, what we have is that you have this G, this last term you have to check is G with the tensor product of logarithmically many terms. Okay, so it's like a vector that can be expressed as the tensor product of log terms. And you can also think of this as a polycommit for a commitment that has this form. So then the main idea is the usual idea when you cannot get around something, if you cannot beat it, you amortize it. Okay, so that's a bit the idea. So if we look a bit closer at the verifier of bulletproofs, we can identify 2 parts. Okay, so as I said, GMU doesn't have to really be part of the proof because the verifier can compute it itself, but it helps to understand what's going on here. We have a verifier, and there are actually 2 parts in the verifier. There's like a succinct part where you just would be verifying every round. Like it's the whole rest of the proof, except for the part where you're checking that GMU is correct. Okay, and this is really a succinct thing. And then there's like this thing that's causing us trouble, that's just linear. So we have like a verification predicate, and we can split it as the conjunction of 2 different predicates. No, this is like the output of the full verifier is the output, the end of these 2 bits. Now, there's another thing here, which is like, if we think of this G mu as a polynomial commitment, actually the opening of this polynomial commitment is very fast to compute. Okay, so let me explain. So here, when we have to compute so here we cannot exploit the tensor structure of this because this is a multi-exponentiation. Okay, and we have somehow we don't have any relation between the G's, so we don't know how to exploit this fact. But if I'm trying to evaluate this polynomial in a point, I can do that in logarithmic time, right? Because this is just a product. Okay, so this gives me yet another thing that I can check succinctly. Okay, so this gives to this leads to this strategy. So imagine, like, again, I have no motivation for now because I'm trying to avoid talking about recursive proof composition and things like that. But imagine that for some reason we want to sequentially prove many of these inner product statements. Yeah.
I don't know, maybe it's a silly question, but I missed it. So why is it this fast, the last check?
Oh, yes. I actually thank you for interrupting because that's very important. Okay, because this is just a field element and this is just a product. So S is a field element. It has to, you have to compute this power, like this is at most n. Okay, so this is logarithmic in n with square multiply, and this is like a product of new terms in the field.
Yes. What is n?
N is the size of the n is the size of the commitment, and n is 2 to the mu.
N is 2 to the mu. Okay.
Yes.
Yeah.
Okay. So
Mu is the number of rounds.
Mu is the number of rounds. So yeah.
Like this polynomial is only for structure setups, right? Or how
No.
is experiencing what happens with
This doesn't play a role. So like the key that you're using doesn't play a role. Like you can see it here. Okay, this is why I enroll it. So what I'm saying is, like, if you write this univariate coefficients, this univariate polynomial, and you look at its coefficients, and so these coefficients are the same as the coefficients that are here. So this is a commitment to this polynomial with this key. So in some sense, it's like a commitment to univariate polynomial, but with a multivariate key. Okay.
Yes, but like then there is only an X, while I would like to evaluate it in like G0, G2, G1, like on different points.
No, I want to evaluate it in S.
So you're saying computing the polynomial commitment is expensive, but evaluating, once I have it, evaluating it in S is fast. Or
So no, not once you have it. If you know the alphas, so the verifier doesn't have the polynomial, it doesn't have the full thing.
Yeah.
Never opens G mu. That would be linear to know all the coefficients, but it knows a succinct description of G because these are the challenges.
yeah.
So the idea is, like, if you have a succinct description of this polynomial, so you know the alphas, then evaluating is super fast.
But
Super
the
fast.
verifier doesn't know the alphas.
Yes,
That's
because
what
are the
they are.
challenge.
Yeah,
They are the
that's what they are.
challenges.
What is the thing that is slow, that takes O of n time, or n?
Well, you still have to compute the opening. You still have to show that the opening matches.
Okay, so computing the evaluation of the polynomial is easy, but computing the opening of the commitment is hard.
To prove that the opening is correct is not. Okay, so maybe let's take some time to, so the final thing is this, it's also the final slide, so we have, so what we are doing is this, okay? We are like, the main idea is that there is a part of the proof that I don't want to do. I want to prove many different claims, no? Claim one, claim some, so I want to prove that this is an inner product, that this is an inner product relation. Okay, I want to prove this sequentially for whatever reason, doesn't matter. And now the main idea is that I will delay part of the proof. There is one part that I don't want to do because this will cost me linear time. and I want to amortize it and keep it for later stages, okay? So let's see how do we do that. So the idea is, so let's say you have a claim. You want to prove that C1D1 is an inner product relation. Now, you give a proof. No, like what's the proof? This has logarithmic communication. It consists of all the succinct part and the last group element. What do we do? First, we check all the succinct things we can check, which means verifying that all the rounds are correct, blah, 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 okay? Then, what we do, and this is a key, we pick our point at random, okay? So this is an interactive plot. So of course, the prover doesn't pick it, so he gets it as a challenge, but he gets as a challenge a random point, okay? And then the part that he didn't check, so what's the linear check, gets reduced to saying this polynomial, this value is a polynomial commitment to this element.
That's the.
So that's a new claim. He can compute the new claim because this is fast to compute.
Yeah. What is pi?
Pi 1? No, sorry, this is the product.
The product.
It meant to say that this is a succinct. It can be.
Ah, yeah. It's a big pi. Yeah.
Yes, sorry. Okay, so the new claim is this thing is a polynomial commitment to this value that I can compute.
Yeah.
Okay, and what do you do in the next stage? Okay, you wanted to prove this, but you wanted to prove a new inner product relation, but you transform it into proving a new product relation and also proving that these two things, so this is what that G1 new is an opening, so opens to GS1. Okay, this is a polynomial commitment, but I already said that a polynomial commitment is a sort of an inner product relation. Okay, and you have to believe me here that I can batch many inner product relations and do it simultaneously. It doesn't cost me much. Okay, so essentially I have a new inner product relation that's like a bit expanded. It has more terms, but it's essentially the same cost. And then now I would run the proof and I get a new value and you start over again. So you always keep delaying part. So every time you're reducing the claim that this is correct to a new inner product statement that is like fresh and you prove it in the next round.
Is the second claim now twice the size of the first claim?
Yeah, well, it includes some extra terms. It's not twice. These are 3 group elements. This is 1 group element and 1. So these are 2 group elements in 1 field. This is 1 field and 1 group. But the point is that it's okay. Like this doesn't matter, right? Proving 3 statements or proving 4 statements. In fact, you batch it, so it doesn't even affect the communication complexity of the protocol. But even if you don't believe that, just think that the proof will be 4 times longer, but that's still logarithmic. Yes.
Just to understand, at the end of the day, you still do a linear check, but you're amortizing over many instances.
Yes.
So it only makes sense if you're amortizing over n.
Yes.
Yeah. Or, well, it doesn't have to be n, but it should be more than constant, certainly.
Yes. And that's what people, I mean, I guess Anka will talk about this and what do people use also for doing recursive proof composition, which essentially a recursive proof composition is where you're doing a proof of a proof. Okay, so you're proving that you have a proof of a previous statement and that something new is true. Okay, so like the idea is you don't want to have this linear part in the claim, so you keep postponing it until the end of the recursive proof composition. So that's I think it's 9:15.
It's a beautiful slide to end on.
But today it was really time, everything. Okay, so I think that's like a really important technique. It's also not easy. It's used in different contexts. It's also used in the pairing-based setting. maybe I'm saying too much because it comes in after the break, but in the pairing-based setting, you have to think that this is actually some constant size to verify. Okay, so anyway, so that's it. Sorry.